So in case of NLP, when we want to use NLP for text, I mean, we have two options. One option we can use convolutional neural network. The second option we can use RNN. We can use CNN when we have a text of fixed size. Of course, the text is not fixed, it is not of fixed size. So in this case, we need to decide what will be the length of my sentence or my paragraph, for example, my text. So in this case, for example, in internet movie database, they choose the length of 10,000, maximum length of 10,000. So in this case, each review will be represented by 10,000 words. So in this case, we need to drop all other words. We need to keep only words which appear in the dictionary, which we find, because we will use a dictionary of 10,000 words. How can we select this? I mean, you can just you can make some coding, and this coding you will find the frequency of each word. How can we find the most popular words which are used? We can build a dictionary, and we can use the most frequent words which appear in my reviews. So in this case, we will drop the rest, and we will keep only 10,000. So the maximum length of each review will be 10,000. We will use one-hot encoding, so we will, I mean, the vector will be, all values will be 0 except where we have a word, that word from the dictionary. So it will be like this. Not all reviews have the same length, so maybe some reviews are very short, some reviews are very long. The one which is short, it will be what the vector, it will be represented by a vector of the same length, but it will have many zeros. So we're adding lots of zeros. And if it is too long, we will drop out other words, which is not important. We will keep only 10,000. So in this case, we will be sure that we have a sentence of fixed length. We will have a vector of numbers, because neural network cannot work with words. We need to replace it with numbers. So in this case, we can use one-hot encoding for solving this problem. So neural network originally designed, the design purpose was to enable machine learning to quantify input. So the field has grown from just learning classification and regression to be able to generate even text based on unseen input. So in fact, we can use neural network for generating text. For example, chatbots. So you just ask a question and it will generate long answer, for example. So translating a new phrase to another language, generating response to questions not seen before in chatbot, and even generating new text based on the style of a particular author. Some years before, some people they built machine learning for generating scientific papers, and they have been testing it. So they use the code for generating the papers, publications, and they send those papers to journals and the conference, and it was accepted because it looks normal. But all text was generated. So in fact, you can train a neural network to your style, your writing style, and you can just ask the neural network to generate a text. It will generate a text. It looks like a text, but when you read it, you will get nothing from it. But it looks very scientific, and it has some equations, some figures, but it doesn't have any. It does that, and it's very tough for even reviewers. Because maybe some people they cannot, I mean, admit that they don't understand the text, so they just accept it. So some of those papers were accepted, in fact, and it was big scandal because those papers, the scientific papers and reports, were generated by neural network. So, for example, if you have a report at the end of the semester, you can just train a neural network new writing style, and it will just generate it for you. So in this case, it will be sequence to sequence. So the sequence has different length. Even when you translate between Russian and English, for example, maybe the length will be different. Because I mean, each language is different. Sometimes we have very small words. When you need to translate it, you need a long sentence to explain it. So sometimes we have those differences. So in this case, we have a known length of sequence translated into a different length of sequence. So to be sequence to sequence. When it's sequence to sequence, in this case, we need to use recurrent neural network. But if the length is fixed, but in this case, we need to do some work, right? We need to select, build a dictionary, and select the length of each sentence, for example. In this case, you can just use CNN. Today, we need to know how can we use CNN to work with text. We know how to use it with images. Today we need to know how to use it with text. So language, it has a special nature, for example. So the nature of words and their secrets are correlated to the relationships of each word. I mean, when you read something, I mean, there is some connections between words. Even sometimes you can predict. So you can just say something and you can predict what will be the next one, because there is correlation, and we have been learning this for a long time. So even when we were younger, we have those exams in elementary schools. You have some missing. Do you remember those words? So have some missing word, for example, you need to fill up those missing words, because we can predict, in fact. Maybe predict to study. So the relationship can be expressed in at least two ways. We have word order and word proximity. So we have those, the order of words, and if we change the order, the meaning will be different, right? So word order, here are two statements that don't mean the same thing. For example, the dog chased the cat, and the cat chased the dog. When you change the order, the meaning will be totally different, right? So even in, I mean, there is something very famous for when you are writing something in newspaper, for example. So if you said a dog, when a dog, how do you call it? Bite, yes, sorry. When a dog bites a man, for example, it's not something fancy, but when a man bites a dog, right, it's something maybe people will be interested to read about this story, right? So the order is very, very important. And to work with order, I mean, the order is very important, and we will know how can work with order in convolutional neural network. If the language is written from left to right, or from right to left, right, from up to bottom, so how can we deal with those kind of text? Also, word proximity, for example, and this is something maybe it's. So you have a long sentence, for example, and you have some word here which is related to this one. So this is something very difficult, in fact, right? So those relationships can be explored for better in two ways, especially and temporarily. So it's about the order of words as a direction. Should we go from left to right, from right to left, from top to bottom, and so on? Temporarily, it's when it's a spoken language. You don't know what will happen, and you don't know the length and the context. What is the connections between different? So it's about word proximity. So in the former, you examine the statement as if it is written on a page. You are looking for relationships in positions of words. In the later, you explore it as if spoken. The word and letters become time series data. When it's spoken, it's like time series data. And therefore, it's much better to use RNN to work with the spoken language. So if you need to translate something, so. Also, these are closely related, but they make a key difference in how we will deal with them with neural network tools, right? So I mean, this order and special data, for example, is usually viewed through fixed points window. We need to use this fixed window all time because we're working with neural network, and we need to define number of inputs. Time series can be extended for a known amount of time. I mean, if it is time series, we won't have this limitation effect. We can just work within length of data. So the two most important choices for natural language processing: convolutional neural network and recurrent neural network. And of course, there are lots of variations of those two types. How are you passing tokens into the neural network? You need words to be represented as numbers. I mean, neural network are working with numbers. We cannot work with words. It will not be able to understand it. So in fact, we have to maybe use one hot encoding or word embedding, right? Both are almost similar, right? So it's just the length of the picture, because we need to change. I mean, if you need to work, in fact, this is correct for RNN and CNN. We need to represent words by replace words by numbers. If you are working in images, we have pixel value, and the pixel value is a number, right? But words, we cannot work with words. So we need to replace words with numbers. So because we need to do some math on it, so in this case we need to represent it by words. by numbers. So one hot encoding, we know what. So we will have a vector which has 0 for every possible vocabulary word you want to consider with a 1 in the position of the word you are encoding. So for example, you want to say, how are you, for example. So how are you? We need to decide first. What will be the length of my sentence, right? How are you? If it's a 3, for example, so in this case, we will represent each word by 1 vector, right? So if we need to represent it by 1 hot encoding, we can just say, for example, how are you today? How? I want it to be 4. How are you, for example, today? So we need to decide what will be the length of your sentence. If your sentence will consist of 4 words, so in this case the length will be 4. So now we need to represent each one by 1 hot encoding. So how, for example, I can just represent it with a vector. This vector will have a length or size of 4, and it will be 0 everywhere except in that location. So this one will be 1, right? I mean, the order it may be. I mean, the order. Of course, we need to have a list of words and based on the order in the dictionary. For example, how are you? For example, or it will be also like this one. It will be 0 everywhere except in that location, right? Right. Yeah. Okay. Yes. So it will be like this. You, for example, it will be the same. So in this case, we are using 1 hot encode. So it will be 0 everywhere except in that location, for example. So in this case, we will represent it using this one. So in fact, you can just imagine now that we are converting this one. It's a 4 times 4, right? So it's a square matrix. You can just imagine that we are converting this one into what? Image, because this is a symbolic image now, right? So now we are converting, in fact, words into matrix of values, or we can just say it's image, for example, right? So it's similar to image. So now we can work with neural network. So 1 hot encoding, the vector has zeros for every possible vocabulary, with 1 in the position in the word you are encoding, for example. Word vectors, I mean, this is another way for encoding words. So we call it word vector or word to vector. So in this case, in fact, we train word embedding model. And this word embedding, it's a neural network like this one, like autoencoder. The input will be hot encoding or multi-hot encoding vector, for example, and the output will be the same. I mean, the output will be the same length. It's softmax. I don't know. The output should be here. The output will be the same length, but it will be float numbers, right? So now we are converting this one from this mode into this mode. No, this one should be less, in fact. Oh, yeah. Okay. I need to check this. So, for example, we have 1 hot encoding for maybe for 1 word, for example, like R, for example. And after training the model, right, we will train a model for doing this word embedding. And we will have this one, we have number of weights, just multiply. You will convert this one from this size into a smaller size. So word embedding, in fact, it's like coding in autoencoder. It's the same. We train autoencoder for dimensional reduction, for compressing the data. So in fact, instead of using, because this one, as you can see here, when we use one encoding, it's fixed length vector, and the vector, most of the values are zeros, in fact, right? Most of the values are zeros. So imagine that this one is 10,000, right? 10,000, it's too much. So my model, in fact, will be complex, and we will have lots of zeros everywhere, so it doesn't have any information, in fact, except few, 1 values. The rest of the values will be zeros. So it will be very tough for training a model, in fact. So instead of working with this one encoding, we can use word embedding, and we can get this word vector. So this word vector, it will be lower dimension. So it's like compressing, as we did before with autoencoder. So in autoencoder, we did the same effect. We have some inputs, and we try to use autoencoder for dimensionality reduction, for example. So we can represent it with more compressed vector. So we can just decide what will be the length of this one. And this one now it's representing this one, and all those values here are float values. So this one, it's more efficient way for representing your words. So in this case, I can represent each word with 3 values, 3 float values. Those values will be different, so we will have unique value for each word. So in fact, we can train word embedding neural network as a word embedding similar to the autoencoder. Yes. So passing the tokens into the neural network, for example, we have some inputs. So if you have a neural network, I'm talking about the order. If we change the order. So for example, if we have a sentence like this one, see gem run, for example. If we have those, we have some weights here, right? So and each one of those, we have those sentence or vector, for example. When you multiply those values with those weights, we will get some output, right? If you change its order, what will happen? So we will have different values multiplied by different weights. So we should expect different results. So maybe it's a review, for example, and if you will use it in the order, in the same order, maybe it will be positive. If you will change maybe the order, it will be negative because it should have different meaning for them. So
in RNN, maybe order matters.
In
recurrent neural network, maybe order matters.
It doesn't matter?
It matters. Maybe
it matters.
We are like considering the last word. But if we are dealing only single word, maybe it will not affect.
It is word by word?
Yes. If we are not considering the last word,
yes,
no connection between the words. For example, if we just classify based on the, for example, we are doing the semantic analysis, and based on the expression like sad and something like that. So in that case, do you think the order of words matter?
It will matter because of this simple example. We have some weights here. We change this one now, this one train, and we have the weight values here. This one has a value, this one has a value. Correct? We have here different values. So if I multiply this one by the weights here, it will make different contribution if I just move this one here and this one came here, right? Just imagine this one it's 0.9, this one 0.7, and just when you multiply, you will get some numbers. When you swap, this one 0.7 multiplied by the weights here, and this 0.9 multiplied by the weights here, it should make difference. It shouldn't, in fact, because we have here the summation.
Yeah.
No, it will make, yeah, because if this one 0.7 multiplied by this number, 0.9 multiplied by this number, no, it will make difference. Because this weight value is weighted some effect. So imagine that this one 0.9 multiplied by 1, this one 0.7 multiplied by 0.5. So the summation here will be different. If we change it this one, so now this one 0.7 multiplied by 1 and 0.9 multiplied by this number here. So the summation here will be different. So in fact, when you change the order, the meaning will be different, and also the conclusion here or the probability here will be different. So it will change. So the order is very, very important in text. So if we swap the order of tokens into something else, a different results may come out. So in CNN, we know that in convolutional neural network, we do those window convolving over function. We have a function or input, for example, and we try to convolve over those functions. How can we do it? We have a window of some size, for example, and this one, it slides over this function or over the data sample or input data. So we know this one. This is just the filter for the kernel, and this kernel is sliding over my image or my input data set. We will do the same. So for example, for images, if we have an image, we have this is my image. We have a filter of you need to decide this filter size, and then when you train your model, those weight values will get some numbers. We initialize it with normal values, and after training for some box, we will get some numbers. So in this approach, we just convolve and move with one step. The step we call it stride, so we need to define the stride, the step size, for the kernel size or filter size, for example. And the padding, do we need to have padding or not padding? It could be same and it could be valid, for example. Valid, which means we don't have any padding. We're not using padding. So this one, maybe it's an image, and we will convolve over the image from left to right and from top to bottom, correct? So this is the order which we use. We will do the same with the text, but we will see how can we deal with it. So For NLP, we need to use also convolutional neural network for natural language processing by using word vectors. We can use word vectors, we can use word encoding. Word vectors, we need to train a model. This model we call it word embedding model. So instead of the image pixel values, instead of image pixel value, we will get some other values. It's not 3 channels, maybe because it's just a text. So imagine you have a paragraph, for example, or E4 page, right? And we need to convert it into word embedding. So we will get one-dimensional. It's 2-dimensional in fact, but we don't have 3 channels. It's 1 channel, like 1 channel, like grayscale image, for example. We will have a matrix. This matrix will be square size, squared. So instead of using image, we will use this matrix, but just imagine that it's an image. So we will see the difference now. Spatial dimension, you want to focus only on the relationships of tokens in one spatial dimension. So should we go from left to right, right to left? So it's according to the language. For example, Arabic, we're writing from right to left, right? In Japanese, they are writing from top to bottom, correct? So the direction is very, very important. So vertical versus horizontal relationships between words in a text. You need to focus on the horizontal relationship for language that are read left to right or right to left, because we will do the same, but the direction will be different. So instead of starting from left to right, we will do it right to left, right?
Like Persian. Like Persian.
And you are writing from right to left.
Yeah, right.
Yes. So we can write something like this one.
Yeah. Bismillah.
Yeah.
Oh, I see.
So we're writing in fact from right to left.
Yeah.
In Persian also we're writing from right to left.
Yes, yes. But mathematics is to start from left in Iran.
So
Mathematical symbols.
which are you using those numbers?
Yes. Yes, exactly.
But it's also from right to left.
It's possible, but we write from left.
Because those numbers they are Indian numbers. We are using.
No, they are not Indian.
No, those are the Indian numbers. But those one, it's the maybe Arabic numbers.
No, they are not Indian numbers.
Those one?
Yes.
They
are Persian.
Persian?
Yes, of course.
Yeah, no problem. So this one, but we use it from right to left.
Amazing.
So this is the order which we use.
In Arabic or
In
in
Arabic, yes.
Arabic. We write from left.
From left to right. It will be very different.
But we have a lot of documents, original documents that is it's our own numbers.
But it's the same numbers. Those numbers.
Maybe. Because in the past, the India.
So can you read this one?
Yeah. Yes, 20.
No, 25.
Yes, of course, but it's close to 20. 25 is like this.
What is
24.
24?
Yeah.
Yes. So in this case, if it is English, for example, you can just go in this way. I mean, when we have the filter and the kernel should move across, it should slide over the image, right?
Yeah.
So you can go from left to right, or you can go from right to left. You can go from top to bottom in all traditional Chinese and Japanese, right?
Yeah.
So this is a question. So how we will move if you need to work with text? So horizontal relationships for language that are read left to right. If we're going top to bottom, because we need to go. I mean, we will go left to right like an image. This is one line, and after that we will go to the second line. So we need to go down, right? So it will be like scanning the same image. So this is a special dimension. If it is horizontal or it is vertical. For example, focus on vertical relations between words for languages that are read top to bottom before reading right to left. Because in Japanese, for example, they are writing top to bottom, and after that we move one line, one column to the right. Yes. So instead of two-dimensional filter, I mean, we have been using two-dimensional filter, right? That you would convolve over two-dimensional input. If it is an image, for example, you will convolve one-dimensional filter over a one-dimensional input, such as a sentence. Because a sentence it's just a vector. If it is one hot encoded, for example, it's one dimensional. So it's maybe it's 1 times 10,000, for example. So it's one dimensional. So we should just imagine that we will have a kernel, and the kernel will be also one dimensional, and it will move from maybe from left to right, or from top to bottom, and so on. The filter shape will also be one dimensional instead of 2 dimensional, as in we have an example here. So we have one if convolution. We have this sentence, for example, right? And this is a filter. So the filter will be maybe 1 times 3. So instead of 3 times 3, it will be 1 times 3, and it will move according to the special dimension which we need to focus on. Maybe it's from left to right. So in this case, it will move like this, scanning your text. But of course, we are not working with text. So first, we need to convert the sentence into maybe one hot encoding into word embedding, word vector. We call it word vector. Because this one, if we converted this one, if we have this sentence, and if we converted this sentence into one hot encoding or word vector, for example, it will be square matrix. So this is a trick. How we will select what will be the filter size. It will be, we will call it also one dimensional, but in fact, in reality, it will not be one dimensional. We will see it. So if you imagine the text as an image, the first dimension depends on the page width or sentence width. So the first dimension, right? And the second dimension is the full length of the word vector. So this one, for example, I mean the dimension of the word vector. Maybe this one we will represent it by 100 dimension word vector. So so in this case, each word will be represented by one vector of size 100, right? Or 10, for example. Imagine it's 10. So this one will be 10 times 1. It will be column vector. Cat will be 10 times 1, different vector, right? This one and so on. So if we imagine it using word vector of size 10, for example, so each word will be represented by one vector like this one. How many ones of those? It will be the total number of words in each sentence, which is fixed because we need to fix it, right? So it will be like this one. So for example, it could be, for example, if it's 10 times, how many words per sentence? How many words? 20? We can just say it's 20, for example, or here it's 1, 2, 3, 4, 5, 6, 7, 8, 9, it's 9. So it will be 10 times 9. It will be like this one. And this one, it consists of 10 values. Those values will be float number. So in this case, my sentence has been encoded into 10 times 9. We call it word vector. Right? So it will be like this one. And each value here, we will not have lots of zeros as in one hot encoding, but it will be much compact. And we will have lots of float values here. So just numbers between them. So like grayscale image, it will be like this. Now we need to be careful about the size of my filter. I mean, we agreed that the kernel will be one dimension. So if it's one dimension, so imagine that it's 3 values. It's one times 3. So it will be like this one. 3 values, omega 1, omega 2, and omega 3. How can we use this one here? How can we use this one here? Is it possible to apply this one here? Is it possible? We have 3 values, so it will be like this one. So for example, it will be, we will apply it like this.
It will be one matrix. It will be one matrix.
This one, the filter?
10 cross 9.
Yeah, this is correct. No. It will be 10 times 3, the filter.
Filter is the kernel we are applying.
Yeah, this is the filter which we need to apply. Can we apply this one here to each pixel like this?
But these all the word vectors will be stored in one matrix, right?
Yes.
We will have one matrix like we have an image.
Yes, it will be 10 times 9. So what will be the size of my filter?
One.
One row?
1 cross 3.
Because if we will use it like this one row, 1 times 3, it will damage my text, in fact. because this one, it represents one word, and I need to scan it like it was mentioned here. So I need to convolve over each word like this one. This one, I'll present move one, strike, check. Okay. So in this case, if I use as a filter with this, in this case, it will damage my sentence, right? My meaning. So it's a simple trick. We need to change the kernel size into the length of word vector times the size of the kernel. So in fact, the kernel, we will just expand it like this one, and in fact it will be 10 times 3. But we will call it one-dimensional. We will call it one-dimensional kernel, but the kernel in fact will be 10 times 3. So it will just expand it, and it will have lots of values: omega 2, omega 3, 4, 5, 6, until here 30 omega 30. So it will be like this.
In each word vector, that the value will be 1.
Here,
Is word, right?
no, it's not 1 and 0. It's not one hot encoding.
Float value.
That will be float value.
Float value and the remaining will be 0.
No, I don't know, because we will train like autoencoder. Remember autoencoder? So if we will train something like autoencoder, they call it word to vector, word embedding, and this word embedding, it will convert each word from one hot encoding into this short version or short word vector. Because if we imagine that we are using one hot encoding, so the input would be one long vector, 10,000 times 1. But not all those values in fact are ones, just a very few. So imagine that I'm saying, how are you? So only 5 values will be ones, and the rest will be zeros. So it's a very sparsy vector. So we will use this one to train one hot word embedding. So we need to convert this one into a shorter one. Maybe this one will be 10 times 1, but those numbers will be float numbers, and we will have one unique vector for each word. So this one will be more compact and more efficient with that. So it's about efficiency if we need to use one hot encoding or if we need to use word embedding. So word embedding, it's like compressing the data into this short vector. So in this case, so the difference here, if you just, this is the only difference, and this is the goal from this today, in fact, is to just understand that the vector or the kernel, in fact, they call it 1D vector, 1D kernel, right? But when we use it 1 times 3, this one will automatically expand it, maybe in the code, for example, into the length of the word embedding. So it will be this one and not this one. In this case, we will apply this one, and we will move by some steps, and we will scan my text from left to right, or from right to left, from top to bottom, according to the special dimension which we are looking for, according to the language. Yes. So you will only be concerned with the width of the filter. This is the width of the filter. In this case, 3 tokens wide. I mean, we will have the wide will be 3, but the length will be the width. This is the width, will be the number of the size of the kernel, and this dimension will be the first dimension of, will be the dimension of the word embedding, will be the height of the word embedding. So as I told you before, we need to use some padding in natural language processing. Since every sentence in the text has not the same number of words, we need to have inputs with the same size. This is very, very important. How can we do this? We need to define the maximum number of words of each sentence, and drop some words if it's no longer important, maybe. So drop words from the beginning of or of the end of the sentence. So we need to drop some words. So you need to define your dictionary and drop the list. And this is what we have done last time with Internet Movie Database. In Internet Movie Database, the length is different from one review to another review, but they defined maximum length, and they made a dictionary. How can we drop? We drop less important words. How can we define that this one is important, this one is less important? So they count number of words in the whole text. They combine the whole text, and they count number of the frequency of each word, and they just ignore or neglect less frequency nodes. So we select the top 10,000. And we say that, okay, those are the most important. We will drop the list. You drop other words. So in this case, we are sure that each review will be maximum 10,000. Some reviews are very short, maybe 10 words. So in this case, we will have some reviews will be represented by one large vector of 10,000 zeros, except the 4 ones. Right? So this is a problem. So we will have lots of zeros. So it's a smart to use word embedding, because in word embedding, we will try to reduce the dimension of this one hot encoding, convert it from this 10,000 into maybe 100, maybe 100. So in this case, I will represent each review by 100 values instead of 10,000. Because the probability, even the model which I trained the last time for internet movie database, it was overfitting 14. It was overfitting because we had this kind of problem. Because one hot encoding is very, very large. And when we use it for a model, and the model will be very, very complex, very, very hard, because we will use this one as a fixed input, so we'll have lots of weights. So the model capacity will be very, very high. It will be a problem because I have lots of zeros. It will not help me in training my model. So it will be really very complex. Maybe the model itself will try to make feature selection, because most of numbers are zeros. We will not be able to train it efficiently. And so it's a smart, in fact, before doing this, to try to use word embedding. And there are lots of transfer learning models for word embedding. So you can just import one by Google, for example, or by Facebook, and you can just use this one for coding your text into word vector. So we can add zeros at the end of the sequence to make the samples in the same size. Even if it's shorter, it's normal, because now I need to represent this one by a fixed length. So if it is 4 words and then my dictionary is 10, so the rest will be zeros. This is okay, right? Because we defined my vocabulary. We need to define the dictionary of vocabulary which we will use. You can just do it for simple example. For example, this example, I can just say, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. I can just say my dictionary will be 9. Maybe my dictionary will be 20 words. So in this case, it will be 1 in the position of those words and 0s otherwise. So now we have a fixed length of a sentence of fixed length. So how we will convolve over text using this approach. So we will call it 1D convolution with word embedding, right? This is my sentence. This sentence will be converted into this one. So we have one vector representing each word. And this one, it's float numbers, because we use word vector. We are not here using word. We are not using word. Yes. So we will have this one. So this is my sentence. If you want to use one-hot encoding, you should imagine that this one will be square matrix. So if this is my list of vocabularies, this one will be 9 times 9, because we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So if we use one-hot encoding, this one will be 9 times 9. So this one will be 9 times 9. But because we used the word embedding, now it's a 6 times 9 or less, right? So word embedding is very, very efficient to work with text. So now we need to see what will be the filter size. It will be 1 dimension, and the dimension will be 1 times 3. So it will be, the dimension of my filter will be 1 times 3, but it will be represented like this one. The width will be 3, which is the kernel size, but the height will be the dimension, the input dimension, or the dimension of the word embedding. So this is a trick here. So now we will apply this one here, and we will move step by step to slide over our image or our input volume text, right? So if it is image, for example, we have 3 channels. It's RGB. So But you can just imagine that this word embedding would be like one vector or one matrix or one image of one channel, like RGB connection. So we will apply this one. Do you see? When you apply this one here, we will get one activation, one convolution, one activation, and we will get one done. We will move it one step, we will get another one, and so on, right? So if you are moving by stride equal 1, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 6, 7. So it will be like, this is one time. We will move one step, 2, 3, 4, 5, 6. I don't know why this one it's 6. Oh, it's 7 values. Yeah, it's 7 values, so it's correct. Because we will move by stride equal 1. So we will start here. This will be the first activation, second activation, third activation, fourth activation, fifth activation, sixth activation, seventh activation. So we will get this one. We will not go down now. We will not go from top to bottom because unless we have a text which is maybe it's T4 text, for example, and we have the end of line, and we go to the next line. We can do it like this. But we need to be careful. So it could be several lines and it could be long text, but you need to be careful about the word embedding because your filter will be the word embedding size times the kernel size. So this is very important. So we will go left to right, top to bottom, right, but with this dimension. So in this case, we are sure that we are scanning the sentence from the whole sentence, the whole word. We are not destroying the structure of each, because if you will use less or more, we will destroy in fact the structure of my text, right? So it will be a problem here. So we need to be careful about this one. So I guess this is all for today. So it's just so the one-dimensional filter can be misleading as you get to a new word embedding, right? So the vector representation of the word itself extends downwards, but the filter covers the whole length of the dimension in one go. The dimension we are referring to when we say one-dimensional convolution is the width of the phrase, the dimension you are traveling across. So it's just yes. So I mean the rest of today will be some projects because some people they made very good progress. Some are writing reports and papers. Even they are writing very good now in some papers. So we will finish here, and the rest of today and next week it will be just a project. And after the exam, you can just continue working in your if you are writing a paper, for example, just continue working with it and try to publish it maybe after the new year, for example. There are lots of conferences. If you need some help, I can find a good conference to you. It could be a journal paper, for example. So you can just continue working with it. It will be very good output, in fact, if you can get publication from the project. So we have something missing. We have the course report. So the course.
Can I ask you?
Yes, please.
Yes, because I know from when you are using CNN, for example, for image detection, the kernels are used different type of kernels, for example, for sharpening, for edge detection.
Yes.
Concerning the text, which kind of kernels, what is their role? What do they do in this text?
It will do something. It will try also to extract some features, and those features we don't know how they will look like, but it will try to understand something. It will try to get some high-level abstract of the text, but we don't know. In fact, I mean, even in image, you don't know if the filter is doing edge detection or vertical or horizontal edge detection. I mean, it will just try to get something meaningful for the problem when we are solving the problem. So if you are working with text, maybe you have two convolutional layers. Those two convolutional layers will try to find some features which make sense for the problem itself. Right, but I don't know in fact which features we will get. Right.
Yeah. Okay. So
we will move across this special dimension, and we will try to get something useful for solving the problem. But what is it? We need to solve a problem and try to maybe plotting those feature maps. Right.
Yeah.
So to be very, very smart, I mean also if we can train a model, for example, and we can try to plot those feature maps, how it look like. Is it text because you can convert it into a text, maybe summarizing, maybe summarization, because you have a text, and if it is, for example, sentiment analysis, maybe the first convolutional layer will try to summarize the text to get something from it. The next convolutional layer will do another summarization. But should we represent it as an image or as a text? I don't know. Because in this here, for example, you will have a vector, right?
Mm.
Do you see this one? Those numbers will be float numbers. So maybe we can do the reverse, and we can try to convert this one back into a sentence or a word, for example, right? So, but I don't know. I mean, we can find distance between this one, because at the end, this one is represented by 6 values, right? So this one will be the feature map, this vector. This one will be the feature map, which we are getting from this one. So maybe we will feed this one to the fully connected layer directly for classification, right? I don't know if it is possible to do one more layer of feature extraction. Maybe one is enough, maybe. But you will get this vector. This vector will be float values, float numbers. So I don't know if this one will, if this output will, you can send this output to another layer for another convolutional layer, or you can just connect this one to the fully connected layer for just if it is sentiment analysis. So I don't know what is the meaning of those numbers. In fact, I don't know.
Yeah. Okay. Thanks a lot.
So, but maybe you can use word embedding and translate this one into a text. Maybe is it possible? So, for example, if we are talking about if we have a story about war and victory and stuff like this, maybe this one will be a word which has a meaning, right? Because we have word embedding, so we can find what is the closest word to this vector. Is it something about victory, right? So if we're talking about text, which is, we have wars, horses, stuff like this, maybe this one will have a meaning from this domain, for example. If you are talking about I mean, movie, for example, which is, how do you call it, horrible movie or something? A movie maybe which is action movie and stuff. Maybe this one will have a word which has a meaning in this. Maybe victory, fight, stuff like this. So in fact, you can test this vector by converting it back into a word using the word embedding. We will do the reverse. In word embedding, we have a text, we have a sentence, and we try to convert each word into one vector. You have a vector here. Maybe you can try to find, I mean, what is the closest word to this one from my dictionary? Maybe it will have a meaning. It could be something which we need to study later. So we need to understand what will be the output from those convolutional layers.
You can always have one convolutional layer. It's always one-dimensional like this.
This one? Yeah, it will be like this, but it will be not this one only for applying it for one line. But if your text has several lines, you will get more lines here. So this one is for one.
You don't just consider it as a one line.
Yeah, this is one line. So we apply the filter from left to right, and after that we will go top to bottom. When you go to the next layer here or the next level here, when we go from top to bottom, you will generate another one. So in fact, after this one, you will get also maybe a square matrix, or you will get a matrix, right? So this matrix, it should be a text, or you can translate it into a text. You can apply a new convolutional layer into this one again, because we lower dimension now. So the dimension of this one will be much less than this one, right? So now we are converting this one from its higher dimension into lower dimension. So this one you can apply another convolutional layer, right? Or maybe, but maybe when we're applying it here, it will be normal like images, right? Could be. So we need to run an example, in fact, and check. But the meaning, because in machine learning, for example, when we are plotting those high-level feature maps, maybe it has a meaning, maybe it doesn't have a meaning. So it should be also the same for the text. So in fact, we need to test this. Yes. So because we finished the course, we need to have a reference group, and this group, it could be 2 to 3 students, for example, and they need to make some evaluation for the course. We need to have one evaluation in the middle of the course and one evaluation after the exam. So we need to do this one now because we were supposed to do it maybe 4, 5, 6 weeks before, but it's too late. But it's better to do it as soon as possible. So please, you need to elect or select maybe 3 persons or 2 persons, maybe people from classroom, people who are online, and the female student. We need to have 1 female student at least in the group, so we can represent all people. And they should write a report about the course. I'm just suggesting, for example, you can list things which you learned, for example. What did you think was the most useful part of the course? What did you like? What you don't like? And digital also, any teaching approach. Is it digital better than hybrid or physical teaching? Which one is better? Because we need to improve for next year, for example. I mean, we have some recorded lectures on YouTube. Is it useful? Right? Do you go back to it again? It's too long, it's short. I need to get some feedback because this feedback will help us in fact improve for next year. Also, the balance between project work, theoretical and concept. Do we have a balance, or was it too much theoretical and the concept? So we need to have a balance between all parts. So also we need to get some input from you. Was anything unclear? How can we make it better? How can we improve? So you can just make evaluation also. If we have a scale from maybe 0 to 5, you can just make some evaluation, for example, right? So it will be very, very useful input from you. So please select the group of this reference group, and this reference group, they should write a report and add their names at the end of the report that are the reference group with their contact information. So I need to submit it. In fact, with NTNU, we need to submit those reports. We need to get 2 reports from each course. If we didn't do it this year, for example, I mean, they will keep asking us to do it next year. Next year, it will be harder to contact maybe many of you. So it's important to do it now. We were supposed to make it in the middle of the course, and we need to have another one at the end of the course. Yes. Also, we will have a new PhD course in 2021. This PhD course, it will belong to EDE, Department of Computer Science. So, and this course, it will be advanced deep learning with Python. So we will try also to do more deep learning, in fact. So maybe this course, maybe next year, it will be more shallow learning, data pre-processing. We will focus on those parts with more examples. So maybe in this course, we will go into deep learning. But the PhD course, we will start from deep learning, and we will try to cover topics from images, from video, for example, text. So it will be more practical, more focused, in fact, because maybe this time we don't have enough time to focus on more bigger examples and bigger projects. But in the PhD course, I wish if I can start with deep learning, so I can start from convolutional layer, recurrent neural network, and all different versions of those models, transfer learning models, and focus more on application side, working with text, working with videos, working with images. So I wish if we can have maybe in the classroom, we will have some groups, maybe some group for computer vision, one group working with video, one group working with text, and because I feel that we need to have a PhD course here in Olson. It's very, very important because we have many PhDs here, and in this corona situation, they don't have a chance to travel to Shanghai and to take courses in UV and so on. So it will be very important to have a course here in Olson. So this course we will start.
Lecture by you?
Yes.
And what is the code for this lecture?
I have the code, but I have the code. I have the code. In fact, I can publish it later on because I just submitted it in EPN, and I'm just waiting them in Trondheim to approve it, so we can publish it because they gave me code. This code I'm just using it for creating the course. So I created it already in EPN, but I'm waiting them in Trondheim to approve it next, maybe this week. And after that, add course description. So maybe it will be next year, and maybe
In the next semester.
spring. Yeah, it could be. If it is possible, if it is not too late, maybe it could be in spring or autumn, for example. I have no idea because we have a system when we publish something in EPN, we should have enough time for. So I will check, but I will inform all people. So, but this course it will be more. I wish that this course will be more practical, be able to work more in projects, and we need to have maybe some directions, some groups One group was working according to each student, each person, each student, PhD work. So if someone is working in computer vision, we should focus from the beginning in project in computer vision. If someone working in text, we should focus from the beginning. Of course, we will have some lectures where we will teach main concepts in more details, but also we need to have some directions. So people who are interested in computer vision, we will have one group, computer vision, one group in text mining and text understanding, one group in videos and stuff like this. And
Time series.
Time series, yes. I will prepare also something for time series, and I will publish it in. Maybe you can find it in Blackboard after exam. You don't have access. Yeah. What about your exam? You will not get
I
exam.
don't know. I send a message to that.
Analysa?
Yeah, advisor you told me.
Yes.
And I didn't get any favorable feedback.
So because you need to take the exam, and I mean because we can fix.
Because at first, I think I have to apply. I have to at first submit my research plan.
It was submitted already.
Yeah.
You have the course not
I-
submitted.
I made it. But I have to submit it. This week I will
But
submit.
can you contact the PhD administration, the PhD program in your department?
Yes.
So ask him that I finished this course and now I will take the exam. So what will happen? How can you register it? Because we can make paper for it. So you can just have those 7.5 study points in your. You don't need to repeat it one more time,
Okay.
right?
Okay. I will do.
So we just talk to them how can we solve it. Just mention to them that you're attending the course and the exam will be after 2 weeks.
Okay.
So you need to take the exam and you can get your grade, and you need to fix it in their system when your application is administered. Yes,
Thank you.
thank you very much. So the oral exam, we will have maybe it will be 3rd and 4th of December. The oral exam. I'm not sure. I will talk. Do you know the exam date?
I think it's third.
Huh?
It's the third.
3rd,
It's not mentioned 2 days, but
3rd.
probably it will be 2
It
days.
will be today, 3rd and 4th of December.
It's online or you can come over here.
It's up to you. If you want it online, if you want to come here, it's up to you. Just up to you. So if the situation is safe, the corona situation is okay, you just come to them here. It will be here in this place. If you want to take it online, it's fine, no problem.
How many questions did you will, for example, ask them?
It will be maximum 20 minutes.
Okay.
Yes, 20, just 20 minutes. Some questions. I have uploaded already a list of questions to Blackboard. So just read those questions and try to revise slides. There will be no questions in coding and stuff like this. It will be questions which can be answered more
About the basic concepts.
Yes. And for projects, for home assignments, we have a project. We will continue today for project presentations, and next week, and we will finish it. And I will send the list of people who has been presenting their projects to Annalisa, so they can find their name in the exam list.
Yes. And please, if it's possible, we will also tell the advisor about, for example, I can't access to the Blackboard.
Yes,
It's better, I think.
but we need to fix it for you because you need to read this course again.
Because already I contacted to my PhD department
And what happened?
and also at the advisor and in your department, and I didn't get any favorable feedback.
Can you connect them together and just make a meeting for both of them?
I don't know.
You can just make a meeting for Annalisa and your PhD advisor. So you can just talk to each other. Right?
Yeah.
How can we fix it? Because you attended the course, you will take the exam, you will get a grade. You need to submit this grade to your PhD.
Yes, of course.
So we need to fix it. So don't need to repeat this one again, or you don't need to attend the exam next year, for example. You can attend the exam next year, but now we finished it. So
No,
yeah.
I did it. Yeah. Okay.
Yes. Okay, so thank you very much. We will take 10 minutes break, and after that we will have one presentation. You can just select who will present first. If you are ready, if you are not ready, we can make it. Next week, no problem. But next week it will be very short, maybe 20 minutes each group, for example. Should we make it like this?
Yes.
So we will close today here, and
I think
okay.
we can continue work on the project today, and then we can present next week.
Okay, so in this case, we will stop here today. Please use the rest of the time for just for working in your project. And next week we will have the whole week will be presentations. The whole day will be just the presentations. Each group will have maybe 20 minutes for presentations, so you have more time to work in your project. It's not a problem for project presentation next week. The most important, if you are really getting good results, just continue working with it and try to write publication from it. Because when you write a publication, it's documentation of your work. So, and all of you are working with nice data sets, good project. So if you can write a good report or publication conference paper, we can try to help also some students to get some money to attend a conference or something. So maybe you can try to get money for the first author to attend a conference and present his work in a conference, if he will manage to get it published. Yes.
I have a question. I have two questions actually.
Yes.
The first is that if you want, I can present something today.
Okay.
It's fine as well.
Yeah, this is fine. Yes, this is fine.
Okay.
So,
and the second question is about the program of the exam. So I followed the lectures and all the slides and so on, but I usually study from the book because I find it's more. I find it easier to study from the book because maybe I miss something from the slides and so on. And I'm using the Deep Learning with Python book, which you have suggested. I'm a bit unsure about which chapters we have to study from that book, because there are some topics which are more detailed in the book with respect to the lectures, and some other topics which maybe are less detailed. So can you give, for example, sort of guideline about the equivalence between your lectures and the books that you have suggested at the beginning, just to have an idea about which are the most important topics to study in your opinion, just to make sure I'm not missing anything.
But in fact, Nicolo, if you use the slides, because I collected the materials from different sources, so maybe it's more safe to just go through the slides, and because I collected things in fact from different sources. So in fact, when I see something nice, I just try to make presentation, make PowerPoint about that part. So this semester I collected many things from different sources. I try to make it maybe it's not very well organized, the slides, but it's covering. When we are covering one task, we try to cover it in the best way with code. So if you can work with slides, maybe it will be more safe.
Okay.
But the book also, which you mentioned, I used many things from that book.
Yeah, I noticed that many figures, many topics were very similar in the book.
Yes.
So, okay. So the slides are complete anyway. So if we study one slide, we can find everything there.
Yes.
I usually use the book just because it is, the book is more discursive. I don't know if this word exists in English, like more detailed. So if I read one page in the book, then I remember the main concepts. If I read one page from the slide, maybe I don't remember some of the concepts, and for that, my memory.
Yeah. Yes. So we can. If people will present today, they don't need to present next week. So we can take maybe 10 minutes break, and Nicolo can present his project. Is there anyone else who want to present today? So it's only Nicolo?
I'm Masoud. I can present today as well.
Okay.
Yeah.
Okay. This is very good. So we have two presentations.
Yeah.
Other people, other presentations today?
Yes, this is Zhichen. Our group can present today also some progress.
Okay, this is very good. So this is very good. So I will prepare a Word file here, so I can just make documentation of presentations. Okay, so in this case, we will take 10 minutes a break, 15 minutes. We can start at 10:15. Is it fine?
Yes, it's good.
Yeah.
Okay. So, and please, if any other groups want to present, just write something in the chat part Just write your names that you want to present, so we can have order. We will start with Nicolo, Masoud, and after that, Chichang. Is there any other groups who want to present? Okay, so in this case, we will start with Nicolo at 10:15. Yeah. So I will make. So now, Nicolo, you are co-host.
Thanks.
We have coffee and tea outside. Ahmed, do you want tea and coffee? Tea and coffee from outside?
No, I just have.
Okay. Yeah. I got a call.
Omar, were you able to run it yesterday? Good.
I ran it, but it is 10 FPS.
10 FPS on CPU. On GPU. I have 15 on mine.
Yes. Okay, so I need to change.
Just 10 something. So,
But it gets heavily reduced when it sees that you have a license plate number. It went all the way down to 5 FPS. I think we can run 2 trends or something like that to just have them on video screen. And then if
Yeah, 27, I'll check my calendar.
lagging,
Because we're finishing pitching anyway, so so I will just check. It's 23rd of 12. Yeah. This is very good. Yeah. This is very good. I mean, the whole day will be fine for me because I just because we finished the teaching 17th, so that day was full of teaching. But now it's fine. 23rd will be okay. So 23rd it's fine from 12 to yeah. This is very good, very good. Now it's in my calendar. Yeah. Okay. Okay. Yes. Yeah. So we need to write a report before this meeting, or should we? Okay. 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 So I will be ready by that time. Yeah. Okay, تصنع خلاص. هذا برافو. هذا برافو.
Vi bara startar uttaget. Eller vi kan ta nocken i starten av och det här är för att snacka sånt.
So, can you talk to each other? Because people are online, you can check reference group. We can select a reference group.
What do you mean?
We need to select a reference group for course report.
Okay.
So we need maybe we need to talk to the people online so they can propose. We need one female. It's important. We need maybe one from here, maybe one online. So we need maybe 2-3 persons. They can show us.
I can do it. Masoud.
Masoud, okay, Masoud. So who else? We need one female from the classroom who was attending in classroom. So we have Masoud, reference group. So Masoud, I will write an email to you.
Okay.
Masoud. Okay, who else, please? We need maybe another 1 or 2. So Masoudi is from simulation and visualization. We need also one female from simulation and visualization. And maybe one PhD student representing PhD students.
I'm not from simulation.
You are PhD?
No, chip design.
Chip design, yes. Yeah.
Yeah, sure, Ibrahim. If you
Okay.
need somebody like no, sure.
Oh, so now we have Amin as representing PhD.
Yeah, but if there is, for example, we don't have any girl now. So if there is a girl, I think it will
No,
be.
we have one
okay.
girl.
Okay.
We have. So we have Amin, the second member. We have. I don't know if she's online or not. Mahdiz. Mahdiz, she is the female.
Yes, she's female.
Yeah, Mahdiz, are you there? Okay. Yeah, she answered. Yes. Do you like to be a reference group member? Okay, so Mahdiz, she will be the third member. So now we have three. I mean, if you want to, but you need to talk to the rest of the people and just write a report, maybe share it with the rest if someone has an input or something. I mean, the idea from the report, we need to get some input to help us also to improve next semester. Right, I mean, positive things and negative things which we can improve. Okay, so okay, so now we Nicolo, can you share your screen and start your presentation?
Can you hear me?
Yes.
Great.
Okay, I need to maybe disconnect my computer because I need to write.
Okay.
If I disconnect my computer, it would be possible for you to. No?
You see me now?
Oh, because we need one computer to be connected, right? Okay, so I will just leave my computer connected here so you can.
Okay.
Okay, this is very nice.
Okay, can I start, so?
Yes.
Okay. So my project is the one that I presented last time, and it is the helicity recognition. The idea in this case is that there are some magnetic fields in the universe. Those magnetic fields are intergalactic magnetic fields, and they also have turbulence. And those magnetic fields can be detected by a detector that is called Fermi LAT. However, in this project, since we don't know which value of helicity those real magnetic fields have in the universe, to train the network, I have used some simulations from a simulator that is called ELMAG, and that has been developed by a professor from NTNU in Trondheim. So the idea is that, the idea of this project is to recognize the helicity sign in intergalactic magnetic field, and this sign can be positive or clockwise, negative or counterclockwise, or zero. And it is also important to consider that the magnetic field strength can have several values according to physics. So we're not sure from a physical perspective about which one is the actual strength. So the theoretical predictions tell that it can be between 10 to the minus 16 Gauss to 10 to the minus 12 Gauss. That is from 10 to the minus 20 Tesla to 10 to the minus 16 Tesla should be. And if the magnetic field strength is low, for example, 10 to the minus 16 Gauss, this means that the helicity is less evident. And so it is more difficult to understand whether it is positive, negative, or zero helicity. And for this reason, performing this analysis by hand is something that takes some time, because in some cases it is very clear whether this helicity is positive or negative, so it is easy to classify by hand. And also the problem is that this kind of classification in some cases is not very precise, because sometimes there are some visual features that might resemble, for example, a positive helicity while it is a negative helicity, and most of the problems are found when we consider the zero helicity. And for this reason, it is very important to use machine learning to have good results in terms of classification. So the idea is that this is the state of the art so far. So in this article that has been published in 2019 or 2020, but anyway, this is a very recent article. The proposal to calculate the helicity value, that is, so positive is 1, 0 is 0, and negative is -1, according to this tool, is to calculate this value that is called Q estimator. So the idea in this case is basically to divide all the points in all the considered points in the plot of the helicity in energy beams. So there will be set of points that go from zero energy to an energy of 0 to up to a certain energy, then a second beam of energy points, and then a third beam. Then I will show an image, and this will maybe be more clear. And the idea is to use a formula that is the Q estimator, and apply this formula to groups of 3 points multiple times. And this means that they perform a Monte Carlo simulation. The problem of this method, of this approach, is that the results are not bad, but the precision and accuracy are not very high in this case, and they perform quite well, only in the case of the 2 classes case. So in the case in which it is necessary to understand whether the helicity is positive or negative. So the problem is that using this method, differently from machine learning, they have a distribution of probability. So this formula applied to groups of 3 points, each belonging to a different energy beam in the initial plot, basically give origin to a distribution that is the distribution related to positive helicity, zero helicity, and negative helicity. That is this one. So in this case, you can see that the blue bars correspond to a positive helicity, the red ones to a negative helicity, and the yellow one to zero helicity. So, for example, if we take 3 points as random, we apply the formula of the Q estimator, And this formula will give a value that is either +1, -1, or 0. And so we add this point to the plot. Then we do this for another point, and we notice, for example, that this point is also, the result of the Q estimator is also +1 for that point as well. And so another point in the blue part. But on the same graph, because this is referred to the same graph, we can have also given 3 points taken at random, that the Q estimator gives, for example, 0 helicity. And the problem is that if the graph is not very clear, and this happens when the magnetic field is quite weak, there is this kind of overlap. So if we take a lot of points, some of them will have a positive helicity, some of them a 0 helicity, and some of them a negative helicity. And this is a problem because in this case, we cannot say with certainty what is the helicity, the overall helicity of our plot. And so, or the overall helicity of the magnetic field associated to that plot. And in this case, the overlap is about 75%, the overlap between the distributions, that is quite high. In the two classes case, the overlap is 50%, about 50%. This means that in the two classes case, there is this curve on the left-hand side, and this other curve on the right-hand side. And this area between, that is the overlap between the two curves, is 50%. And this means that the accuracy in machine learning terms is 75%, something less than 75%, I think. So the idea is to apply computer vision to this problem. Now I will show also a graph soon, a plot, to have a more visual kind of explanation. But anyway, the idea is that the helicity is a visual property, as I will show. And for this reason, I think that computer vision can be applied to this problem, and in particular, CNNs are very good to solve this problem. So the idea, as I mentioned, is to use this simulator that is called LMAG 303, that has been realized by Professor Michael Kahekles. Sorry, I'm still bad with his name, it is too difficult. This is a simulator written in Fortran that is one of the most used, most popular programming languages in physics. And the idea is that the data that this tool generates consists of the position of the particles, that is an XY position, and the energy associated to those particles. So the idea is that, first of all, I want to have some, the inputs that are the outputs of the generators that are the same as the baseline paper. In this way, I can compare the results and say, okay, this is better, this is worse, and so on. So I remove some outliers that are the points that are far away from the center. Right now, I keep 99% of the points that are the more center points. And in this simulation, there is also the simulation of turbulence that is performed using random values. This means that with the same input for the simulator, I get different results because of these random numbers. And so this means that I can generate how many inputs as I want, and have, for this reason, a data set that is as big as I want. The problem is that with many points, it is quite difficult to have to generate them in a short time because the simulation takes a lot of time. So for this reason, I haven't used a lot of points, a lot of data, actually. So the data set consists of 3,564 plots. I I have divided them into train, validation, and test set. These proportions can be changed. I have made some attempts. This one looked quite good, but it is not very not a very common subdivision. So I will try maybe with 70%, 10%, and 20%, as Ibrahim suggested. And there are three possible classes that are positive helicity or clockwise, negative or counterclockwise, and zero. As I mentioned, the zero helicity is the most challenging one because, of course, positive helicity is more similar to zero helicity than to negative helicity, and the same applies symmetrically. And for low magnetic fields, it is quite difficult to make this kind of classification. So now I have some visual example. Maybe I should have put this before, but anyway. So this is an example of clockwise helicity. So as you can see, in this case, the shape of this plot follows my pointer. It goes like this. So you can see that here we have a sort of cloud of points that goes in the clockwise direction, and here as well. So this is why this is clockwise helicity. But as you can see, those points, there is also this cloud of points here, so it is not completely clear. It could have been clearer than this. This instead is an example of counterclockwise helicity. So in this case, you see that the cloud of points goes in this direction and in this direction. And so the shape of the plot is like this, if you can see my pointer. In this case, is zero helicity. So this case is a bit strange because zero helicity in principle should be only a line, but this is what the generator actually generates. And but the idea in this case is that, as you can see, the cloud of points does not prefer any direction. So it is distributed both in the clockwise and counterclockwise direction. So on average, in this plot, the helicity is in fact zero or very close to zero. And those examples were for a magnetic field of 10 to the minus 16 Gauss. That is the lowest possible magnetic field, and that is also the most difficult to classify. So classifying the other ones for 10 to the minus 15 up to 10 to the minus 12 is easier than this, because those plots are much clearer than the ones I've shown here. So the idea consists of taking the initial data, transform those data into those plots where the color represents the energy associated to one point. Then, since helicity is a visual characteristic, it is very important to use convolutional neural networks, since they work with images, and since in this case, it is important to understand the relationship between points. And so CNN does exactly this with convolutions. But it is also very important to perform pre-processing before obtaining the final plot. So in this example, for example, this has not been completely pre-processed. One part of the pre-processing consists of giving the color to the energy. The color scale is logarithmic because otherwise there would have been a prevalence of very blue points, which is not very useful for the CNN. And in this case, you can see that here there is a more yellow part, and the same here in the center, and the same here. The other part in the pre-processing, as I will show, consists of transforming the points using the cubic root, as I will show soon. So there are 100,000 points per image, and this is why generating each image and performing each simulation takes a lot of time. There is turbulence, there is magnetic field strength of 10 to the minus 16 Gauss, and they try to classify with two classes, which is what was actually proposed in the baseline paper, and with three classes that consider also zero helicity. For this magnetic field, the three classes case was not considered because the results were were not accurate at all for this kind of helicity in the baseline paper. So those are my results. For the true classes case, I obtain I use GoogleNet, which is a quite simple network. I started by using ResNet 50 and ResNet 13, and I tried many of them, but those networks are more complex, and for this reason they overfit quite easily. While GoogleNet performs quite well, and it only takes 7 epochs before overfitting. And for this reason, I think this is the best choice so far if compared to the other networks. And indeed, I can obtain good results with respect to the results I had before, because at the beginning, this was 80%, around 80%. Now I obtain 93% accuracy, while the baseline was 73%. Those results have been obtained, as I was mentioning, by performing some preliminary transformations that I will show in the next slides. Let me see if I have the figures. Yes, in the case studies. So if this is the original plot, what I do is pre-processing this plot. So for each coordinate, x and y, I take the cubic root. And the reason why I take the cubic root is to try to emphasize this curvature here and this cloud of points. And as you can see here, this curvature has been enhanced. But I will discuss about those results later. This is the accuracy graph, accuracy plot. As you can see, I have applied early stopping, so on the loss, of course. So when I see that the loss starts increasing here, I stop the training process. So the patience of the early stopping in this case is 0. I have made some attempts also in this case, and a patience of 0 is the one that works better actually. And as you can see, this is the true classes case always. The train accuracy increases quite steadily, and the same applies to the validation accuracy that gets to about 94%. It doesn't overfit a lot because the test accuracy indeed is 93%. It is not much lower than 94%. It is not necessary to obtain 100% in this case because they have several data about the same magnetic field. So by combining those data, it is possible to obtain a better prediction using techniques that are not machine learning techniques. The only difference is that if this accuracy is low, it is necessary to combine more data about the same scenario. Otherwise, in this case, it is necessary to combine less data to obtain a precise result from a statistical point of view. For the three classes case, instead, I obtain a test accuracy of 77%, and this is my confusion matrix. The parameters for the network are almost the same. The learning rate and the learning rate decay are similar to the previous ones, but there are some small differences, and I managed to obtain this result in six epochs, which in computational time don't take a lot of time. You know, on my computer, they take 1.5 minutes for each epoch. So in less than half an hour, I'm done with both of them. Yes, less than half an hour, yes. So the test accuracy in this case is 77%. As I've mentioned before, there are no previous experiments, so the baseline paper does not report the results. But since in the original paper, the test accuracy for the true classes case is 73.5%, and that was an easier case, this is better than the original paper actually, because it is better than the easier case. Again, this is my accuracy for the 3 classes case. I apply the same method for the early stopping, so with a patience of 0, as you can see. And now there are some case studies. I don't know if I'm speaking too much, I hope not. But anyway, I'm almost finished. So the idea is that this is the clockwise helicity. This has been correctly predicted. This is the original graph, and this is the graph after the pre-processing with the cubic root. And this is what I've discussed before, actually. This instead is an example of ground truth clockwise helicity, which has been classified incorrectly by the 2 classes classified. It has been classified as negative helicity, counterclockwise helicity. This case is indeed a bit challenging, a bit tricky also from a visual perspective, because it looks quite symmetric. So it is a bit difficult also for us to understand which kind of helicity it represents. The only thing that allows us to tell this is that, as you can see here, we have a more continuous line here, and here it is less continuous. So this small difference might mean that this helicity is in fact a clockwise helicity, but this is indeed a more challenging case. This instead is the counterclockwise helicity. This is the same graph as I've shown at the beginning, and as you can see, this is counterclockwise because of this, and this has been classified correctly. This graph is is of course related to this because I applied the same transformation to all the graphs, but at the same time, this graph does not have a physical meaning. Anyway, it is possible to notice that there are some features related to the counterclockwise helicity, for example, here and here. But I still don't know why, in which way the neural network has decided to classify this as counterclockwise helicity. To do this, it might be a good idea to use class activation maps, for example. This is instead an example of ground truth counterclockwise helicity that has been classified in the wrong way. It is counterclockwise because you can observe this kind of path. So this kind of helicity, if you follow my cursor. But at the same time, those points here can be a bit misleading, and also here, since it is the same graph that